Hello, everyone. I'm Soonwon. I'd like to thank the organizers for inviting me and giving me a chance to talk about one of the work that I'm very excited about. And also, it's a very pleasure to be here. It's just such a nice place. So today I'm going to talk about quantum convolutional neural network. But before starting, I'd like to acknowledge our colleagues and collaborators. So this work, the presentation will be based on 3 different works done at different time scale. The first one published in Nature Physics in 2019, where we originally proposed quantum convolutional neural network architecture done with Iris Kong. And the next one, Nature Communications paper, where we tried a related approach to the actual experimental data obtained from quantum simulations. And the third one, it has been a couple of years on the archive, but it has been finally published in a journal like earlier this year. And that work is done by Shankar and Ethan. So let's get started. So to this audience, maybe I don't have to explain why it's such an exciting time for AI plus quantum. So let's go very quickly. So AI, I'm not an expert, honestly, but I can obviously tell there's amazing things happening there. In quantum science, I have contributed to the field, but in my view, this is also extremely promising time because we have developed large-scale quantum devices. The first picture is a picture of literally 6,000 atoms, each serving as a good qubit. And the second picture is the picture taken from Continuum, which is a company, and they build one of the highest entangling gate operations. Maybe it's already outdated. Maybe we have a better gate from different groups. And third one is a picture taken from Harvard group, like Misha Lukin's group, done in collaboration with the various other groups at Harvard and MIT, where they demonstrated amazing capability to move atoms and utilize that to realize logical operations and look at quantum error correction and quantum detection. Okay, so that's the background, but to me, those two pillars of the field represent a new method to process a large amount of data. On the other hand, the quantum science represents a new method to produce data from extremely complex systems. Therefore, it's such a natural thing to combine them together and then try to understand if there's anything interesting happening there. So naturally, we talk about machine learning and quantum physics. However, as a physicist, I'm not happy with machine learning because oftentimes we don't understand how it works. At least I lack intuitions. And also, I'm curious whether machine learning would have any application to near-term quantum computing or quantum applications. Also, I want to see maybe there's a deeper connection. Again, there's evidence that there's a connection between machine learning architecture and the theoretical physics. And also maybe there's a connection to quantum information. And these are the topics that I'm curious and partially answer in today's my talk. So of course, I'm not going to give you the answer, but I'll tell you the outcome of the attempt from our work. So with that in mind, please understand that today's talk is going to be basically not machine learning, but me learning from AI. So let's get started. I'm going to summarize our results first and then go into the detail. The first, I'll just briefly review a quantum circuit architecture we proposed several years ago that we now call a quantum convolutional neural network, and then show that this particular architecture has been found useful for a certain task that we call quantum phase recognition. And then later we developed a rigorous theory showing that in fact this architecture is really good and probably good for quantum phase recognition in a broad class of systems. And then we'll talk about how we work in the real world data, but only very briefly. The majority of my talk will be first 3 items. So quantum convolutional neural network, this is done by Iris and Misha Lukin. So before talking about quantum convolutional neural network, let's very briefly recap convolutional neural network. So this is a version of deep feed-forward neural network. And it's best to explain what it is by simplified picture. It's like real world convolutional neural network is way more sophisticated, but let me just drastically simplify. Say I have an input like picture of cat or dog, and I want to recognize whether it's cat or dog using our ML technique. What I do is a sequence of the data processing. And this data processing made out of different types. There's a layers that called the convolution, layers called pooling, layers called fully connected. The convolution part is very easy. It's basically filter function. We generate a new picture where each pixel value is determined by some linear combination of the pixel value from the previous layer. And once we fix these parameters, the linear combination of weight, we use the same weight for every pixel. Therefore, we generate a new picture. So that's the convolution layer. We do several layers of that, and that will maybe blur the wave function, blur the picture in general. Pooling layer introduces nonlinearity. Suppose, as an example, suppose we have a 4x4 pixels, like each number representing the value of the pixel. I produce smaller 2x2 pixels image by taking, say, the largest among the four. And taking the largest value is a nonlinear transformation. Of course, there's other versions of performing nonlinear transformations. After pooling, we do another layers of like convolutions and then layers of poolings. Sometimes we just duplicate the images to extract the different features. At some point in the end, we just a fully connected neural network that's trained and eventually get the recognition of cat and dog. So that's a very simplified version of convolutional neural network. And turns out it has been extremely successful for the tasks such as image recognition. So the key concept in this convolutional neural network is a layered hierarchical structure and successful pattern recognition. And what we are going to do is, in some literal sense, we are going to quantize it. So how do we quantize it? We assume our input is given a quantum wave function. But I want to emphasize I'm given the wave function on a tray of qubits, but not the wave function entries, like numbers. Like it's not a description of quantum wave function, but quantum wave function. So we need to handle this information with a quantum device to start with. As a convolution layer, we apply some layers of local unitary. Maybe you can set all the unitaries to be the same for the local sites, similar to this parameter sharing in the convolutional neural network. Once you use some layers of convolutions, what we do is we perform measurements on a fraction of qubit. And depending on the measurement outcome of the fraction of qubit, if you measure those qubits that's being measured, will collapse the wave function, and we usually throw them away. We are not, it's already in a collapsed wave function. Depending on the measurement outcome, I'm going to apply some unitary V that could be different depending on the measurement outcome to the unmeasured qubits. And the number of unmeasured qubits will be now smaller. So we reduce the feature. And this is what we call like, quote unquote, like nonlinearity. And then do another layer of convolutions and then pooling and depth D. And finally, we apply some fully connected layers, some small enough unitary, but like arbitrary unitary, and optimize it. And then we perform measurements. And we want to use this architecture to do some interesting tasks. It's again layered hierarchical structure, hopefully successful in pattern recognition. And I argue that it is. But before we move on, let me make one comment. I said already that it's a nonlinear, quote unquote nonlinear, because it involves measurement. In fact, that's not precisely true. Because whenever we have any measurement and feed forward, we could just replace this measurement and control as like conditional unitary operations that condition the measurement outcome, and then delay the performing the measurement. Functionally, we can write down the unitary circuit that does exactly the same thing by both delaying the measurement outcome. Written in this way, we can actually delay further until the end. That means we don't even look at them and just measure the measurement outcome. Therefore, this convolutional neural network architecture we have is some structured special unitary. But we don't optimize over all 2 to the n by 2 to the n unitary for the n-qubit systems, but rather a very structured circuit. So we are in some sense constraining the type of operation we can do compared to applying the general unitary. And this also gives us some insight. First of all, because we have a jet subset, but we reduce the parameter from exponentially large in number of qubits to logarithmically small in n, we have a doubly exponentially reduced number of parameters. So it is non-trivial. That's on one hand good because there are so less number of parameters to optimize, so it's good for training. On the other hand, we should be concerned whether it's powerful enough to do any meaningful task. So that's the non-trivial question. On the other hand, it also means maybe the implementation of this is maybe easier, relatively easier. And the final comment is, when I say nonlinearity, in quantum mechanics, nonlinearity is achieved by reducing the system size. Effective map for the different system size could be nonlinear. However, it has to be linear operations at the level of global wave function. But we can talk about that like in the break. So, is it expressive enough? So, to test it out, we tried this algorithm for quantum phase recognition problem. So, what is the problem? This problem is the following. This is a task. Given a quantum many-body system in its ground state, I'm given the set of qubits in its ground state wave function. We ask whether this ground state belongs to a particular quantum phase P. Okay? Say this P could be ferromagnetic phase or a magnetic phase. And this is an intrinsically quantum problem because the input is already in the quantum state. We are not given the numbers describing the wave function. It's just literally quantum state, maybe produced from experiment. So example, so we have wave function given from the experiment. We ask whether it belongs to a particular quantum phase, say Z2 spin liquid phase. We ask whether it corresponds to the phase that's the same as valence bond solid, or is it ferromagnetic? So those are the type of questions that we are going to ask. And the answer is binary. No, it does not belong to the phase, or yes, it belongs to the phase. So it's a properly formulated at the computer science problem. So for example, how to recognize a ferromagnetic order phase? So in some abstract sense, suppose you have a Hamiltonian parameter lambda 1 and lambda 2, and there's a target phase, ferromagnetic phase, and some other phase, say paramagnetic phase. And how do we today? What we do now is just measure order parameter. So you are given the wave function, I'm going to measure magnetization. Sometimes maybe it's in a superposition of two different magnetizations. It's okay, we measure long-range correlations, MIJ. And whenever this phase belongs to that particular target phase, the magnetization will be non-zero, or the two-point correlation function will be non-zero. If this wave function belongs to a different phase, this order parameter may be zero due to symmetry. So this is a valid algorithm. Okay, measure magnetization. That's a valid algorithm. However, this task becomes difficult when we are given the wave function that's closer to the critical points. Because what happens is that if you perform the measurement outcome, each measurement outcome will give you some magnetization, but it has a lot of fluctuations. So it could be maybe like net positive, but it may be like due to fluctuation. So you need to measure many times. So the amount of statistical fluctuation, and then fluctuation is usually amplified near the critical point. So we want to minimize by repeating the experiment many times to reduce the amount of fluctuations. And then tell whether it's zero or not. And that notion is called the sample complexity. You need to measure many times. So the sample. The second one is, this idea is usually good for phases like spontaneous symmetry breakpoint phases. However, certain phases, such as topological phase, symmetry protected topological phases, the notion of order parameter is not a point-like local observables, but it's like a string-like observables. And it's not obvious how to average this order parameter when it's like string-like, because there are not that many sites. So these are the tasks that we want to address. So we are aiming for SPT phase, symmetry protected topological phase in 1D. Okay. So what we do is this. We want some quantum state that go through a quantum circuit in our architecture, and circuit is specifically designed to recognize a phase P, a target phase P, and we measure 1 bit. And if the expectation value is 1, so it's always like say 0 value, then we say, okay, it belongs to the phase, yes. If the measurement outcome is expectation value 0 or like random up and down, then we are going to say, okay, it does not belong to the phase. That's what we are going to do. And this QPR, the quantum phase recognition algorithm, needs to satisfy certain conditions. First, we want the correctness to be guaranteed. I want this algorithm to be correct. Second, I want it to be universal. I do not want to design an algorithm or quantum circuit that's tailored to the particular parameterization of Hamiltonian. I just want the circuit works for the particular phase P, independent of the detailed parameterizations, up to like symmetry representation. And also I want it to be sample efficient, like that's the goal of like reducing it. And I want this circuit to be entirely unitary in a way that we can in the future, if you have a universal quantum computer, plug into the quantum computer so that we can use as a subroutine or bigger algorithm. And in this work, we achieve like large portion of that. The sample, yeah, that's right. Okay, so let's move. But only, it works only for a certain subset of phases. Yes, Christian.
Just to understand, are you attaching this to a specific architecture right now? So are you working on the very atom computer generating your wave functions from that, therefore not to worry about the initialization of the measurement, or is this just all theoretical?
It's all theoretical work. Yeah, that's right. Not married to any particular platform. Yeah. Okay, so as a toy example, we consider a particular parameterization of Hamiltonian now. So it's a Hamiltonian, it's a famous Hamiltonian, it's a paradigmatic model for SPT phases. So we have a spin chain, and Z and X are the Pauli operators, and then we have a J, H1, and H2, like 3 parameters. And I obtained this phase diagram as a function of H1 over J and H2 over J using the DMRG. So this phase diagram is not very curious. It's a well-known phase diagram. This system has Z2 cross Z2 symmetry. One is flipping X on the even side, and the other one is flipping spins on the odd side, and they have an independent Z2 symmetry. When this parameter H1 and H2 equals 0, Hamiltonian only consider ZXZ. You can convince them yourself that this has all commuting terms. So ground state is exactly solvable. It's called the stabilizer state. And it turns out it's a 1D cluster state. When H2 equals 0, when H1 is not equal to 0, then still it's exactly solvable because through the Jordan-Wigner transformation, it maps to 2 decoupled free fermions. And our aim is to recognize, but otherwise, when H1 and H2 are both not 0, it's a generic Hamiltonian. Our aim is to recognize this SPT phase, the red phase. And this phase also considers 1D AKLT phase if you deform the Hamiltonian. I'm going to just tell you the solution. This is the solution. It turns out we have not used any training. We obtained the analytic solution. The analytic solution looks like this. It's a circuit diagram. I'm not expecting you to follow the circuit diagram, but I just want it to be concrete. There's a layer of unitaries. This dot connected to dot means CZ, and this XXX represents so-called Toffoli gauge, but in X basis. And there's a pooling layer. You measure X, and depending on the measurement outcome, we apply Z on the remaining one. And we repeat these D times. So each layer of convolution and pooling measures 2 out of 3 for every unit cell. Therefore, it reduces the system size L to L over 3. And after repeating D times, we measure we apply fully connected layer, which is also a layer of control Z gate. And then we measure one of the spin in the X basis. Our claim is that this expectation value of the final X measurement outcome with a sufficient number of depth will be near deterministically 1 if it's in the SPT phase and otherwise 0. That's my claim. So we try it out numerically. So the bottom right is a phase diagram. So here we consider the wave function for H2 equals 0, but vary H1. This is a free fermion case. And this is the expectation value of the final outcome when we do not apply any convolution or pooling layer. So it does recognize some phase. However, if you apply one layer of convolution and then pooling, the curve looks like this. So it looks a little better. If you apply twice, it looks like this. And if you have 3 layers, it looks like this. So very sharply recognizes phases. And the fact that it sharply changes means our measurement outcome is near deterministic in when it's SPT phase. So maybe this is solvable point. Let's consider a different scan. Let's just H1 equal to 0 and H2 scan. And this looks like this. So different layer, we see very sharp change. In fact, along the generic curve, we also correctly recognize phases. And we can reconstruct basically the phase diagram based on our output of the layer. This is depth 1. But if you have a depth 2, it's very sharp and then it becomes almost indistinguishable from the original phase diagram. But I want to remind you that our circuit does not know anything about parameterization of the Hamiltonian because it's analytic solutions. Yes? So I'm going to explain that. Yeah, so that's right. That's right. So we put there's a fun story. So that's what I wrote that I'm going to do once I start my faculty position. So that was my research statement. But I encountered 2 promising students, and they solved it within a year. So I lost my proposals. Yeah. So, but it took like kind of substantial time to systematically understand how to construct this. This particular example in the original paper, we construct by inspection. Yeah. But I can explain the intuitions. How does it work? So the intuition is the following. We take H1 and H2 as a perturbation applied to J, even though the strength could be order 1. In the absence of H1 and H2, the ground state wave function has a zero correlation and exactly solvable. It's a cluster state. And we define it as if it's a quantum code, some fixed point. And then the perturbations is coherent error that happen to the wave function. So let me illustrate what I mean. We designed this circuit that satisfies the following property. If the input wave function were at 0,0, so it's a cluster state, after the circuit, this wave function becomes cluster state again, but all the measured qubits are in a deterministic zero state. The measurement outcome is deterministic, and it's decoupled, but otherwise the unmeasured one is a cluster state. So cluster state is a fixed point of our circuit while changing system size. If you now consider the wave function slightly away from the fixed point, and then we view them as perturbations, and then what I see is, for example, there's an X operator, that perturbed around the original cluster state. We designed the circuit, so if you push up these excitations or like perturbations in the Heisenberg picture, we perform measurement in X basis, like about Z. So this X measurement will be flipped due to the presence of error, and then correction operator will cancel the remaining Z, such a way that the resultant state is still cluster state without error, but one of the measurement outcome, intermediate measurement outcome, is flipped to 1. So we pump out these, these perturbations to the measured qubit, so that the resultant state is still in a clean cluster state. If you have multiple errors, then we will have a multiple ancillary measurement outcome that turns into 1. While producing the wave function, we corrected many errors, but maybe not all errors. But if you do several times, our hope is that we eventually converge to the fixed point wave function. Once it's fixed, then we are going to perform the conventional order parameters. Now it's easy because we know the wave function exactly as a cluster state, and then verify that it belongs to the phase. And that's the strategy. And what I'm going to talk about now is we just show that this approach can be generalized for all SPT, not all, but all SPT phases in 1D are protected by abelian symmetry. So that's the content of the work done by Shankar and Ethan. Yes?
Can I think of your strategy if, let's say your general state, you can think of it as a quantum pole plus arrow, and then what you do is basically just correct those arrows until you get to the clean quantum pole?
Absolutely. Yes, you just explained my next slide. Yeah. Okay.
So that means that like each of your fixed point the fixed point have to be expressed in some quantum pole.
Yeah. Please do not spoil my talk. Yeah, that's what we are doing. Yes. So how do we provably generalize? So turns out we can show that for every 1D gapped SPT or SSB phase P protected by abelian on-site symmetry, we can analytically construct QCNN circuit that satisfy the following. It's universal, independent of parameterization of Hamiltonian, faithfully correct for sufficiently large system size and depth, sample efficient compared to just naively measuring the string order parameters, and computationally efficient in a sense that the depth of the circuit is generically scaling logarithmic in correlation lengths. But even in the worst case, the 2 star there's some debatable point, and polynomially in depth. So let's go to the details. So we notice the similarity between renormalization group and then error correction. Renormalization group is something that all theoretical physicists love. So the idea is we distill a universal long-distance information out of non-universal UV theory, and by repeatedly coarse-graining the systems. In this way, the fixed point of this coarse-graining procedure is determine the phase matter. Depending on the stable fixed point, unstable fixed point, we have a critical point versus deep inside the phase. And then the operation is usually done at the level of theory, Hamiltonian or Lagrangians. Error correction is similar. We distill important logical information when it's affected by the noisy environment. So like zero, logical zero is encoded like 0, 0, 0. If you just change a few bits, non-universal errors, we can just correct it back. And that similarity is what allows us to make connection between like a phase recognitions. Because RG is theoretically what physics is used to recognize many different phases. So we are going to utilize that. Specifically, in some abstract space with the unknown parameterization, we have a phase 1, 2, 3, and say phase 2 is our target. We can consider a fixed point wave function, and that always exists for each of the phase. And then what we are going to do is when our input psi is given, without knowing what the psi is, because it's given as a formal wave function, I run quantum circuit that it maps to this fixed point wave function. But it's puzzling because different wave functions are orthogonal to one another. A unitary evolution cannot map different points to the same point. But it's doable if you do the coarse graining because your system size changes. So it's an isometry rather than a unitary. And that allows us to pump out the entropy and map to the same wave function. Another challenge is we don't know what psi is. We don't even know the parameterization of Hamiltonian. Nevertheless, we want this mapping of psi to the fixed point for the same circuit Q. And that's where the error correction paradigm is useful. So the strategy is we consider the errorless state and design the error correcting circuit so that all the vicinity of the wave functions gets corrected to the middle point. If you do it twice, you correct for the larger amount of coherent errors, and hopefully if our error correction procedure is good enough, it covers almost entire phase diagram in sufficiently large system sizes. However, we should not overcorrect because I don't want to wrongly correct the wave function in phase 1 and 3 to be phase 2. There was questions? Yes?
Maybe you're going to just talk about this in a few slides, but I was just wondering if I have a wave function, I don't know which phase it belongs to, right? And I assume for different phases, they would require different error correction algorithms. So if I'm completely agnostic of my wave function, which error correction do I use? Does that mean I need to redesign my architecture?
Yeah. That's right. In our approach, we check whether it's in phase P1. If it's yes, lucky. If it's not, let's check whether it's phase 2 and phase 3. Okay. But because it can be run as a subroutine, we can do that search quantumly fast. Okay, so this is the idea. We should not overcorrect. So what we want is a ground state phase diagram to be the threshold for the error correction. That's what we desired features. And that's what the RG and the EC, what I mean by RG equals EC, error correction. I like the phrase, it's fancy. Okay, so we try this for exact QCNN, recognizing gap-1 DSPT phase. So starting from this slide, it's a little technical. So we designed the QCNN circuit Q only depending on information about the phase, but not any other non-universal feature. So our strategy is given a target phase P, we find a fixed point wave function psi 0 first. And this, of course, need not be the input state. We design the quantum circuit such that this fixed point is a fixed point of the circuit up to rescaling of system size, but it should be quasi-local and then symmetric. So they correct by this error, and then any local deformation can be corrected by this Q, and then convergence to the psi 0. Okay. So fixed point wave function for each phase. For the special case of gap-1 DSPT phase has been well studied by using the language of matrix product state. So here I'm using diagrammatic representation of matrix product state. And we can find this wave function. And these wave functions have a nice properties, so-called the zero correlation lengths. If you contract these physical lags and these virtual lags decouple, so the zero correlations. And also for each SPT phase, we can find the box that satisfy the following. If you apply some unitary rotations, like symmetry rotations on the local site, these box relate that property to a pair of fractionalized or like so-called projective representations that lives on the virtual bound. important conceptual consequence is that one local error on the local side maps to the pair of fractional representation, and that will be the primitive of our error correction. It's a redundant encoding of the information. So we'll have a tree hierarchical scale-free the architecture made of convolution and pooling, and then convolution will be of this form. This is like actually exact solution for each fixed point wave function. We just put 6 of them together, and then 3 of the physical legs down, 3 of the physical legs up, and turns out we can show this is unitary. That's our convolutions. And the pooling layer is doing a kind of like majority vote. So, but I have not like explained the details in this slide. So the key point is that the entire circuit of convolution and pooling can be reconstructed by information about this fixed point wave function alone. So here's a proof. If you consider convolution like this, 3 up and 3 down, and then imagine you plug in the fixed point wave function already, and from the property of like zero correlation lengths, what we find is that if you just zoom in, this manipulating the diagram, you deform it, and you see that we have tensors, where the 2 of them are decoupled, but one of them is connected to the left and right, forming a new chain. So this is a proof. So fixed point wave function maps to the fixed point wave function with the deterministic ancilla. On the other hand, if you have a local perturbation in one of the chain, we can redo these calculations where this local perturbations, say unitary rotations, can be mapped to the pair of projective representation. And you see that the one of the measured outcome will have in a different state, and what remains is also in the different state. And depending on the location of error, this ancilla measurement outcome could be different, 1, 0, 0, 0, 0, 1, 1, 1, or in the absence of error, 0, 0. So by measuring this ancilla, we know what type of error happened, like one of the 3 positions. And then we are able to find the error correction operations to undo the computation such a way that the resultant wave function after the corrections becomes error-free, and only error is pumped out from the ancilla. And in that sense, our QCNN emulates our RG flow. So we apply this to the different type of SPT phase. So now protected by Z3 times Z3 phase. Every side we have a Q treat rather than Q bit. And basically we see what we have seen. So across the phase diagram, across the phase transition point, we see very sharp change of our observables. And increasing the depth makes this change sharper and sharper. So basically it works. I want to make a couple of comments on experiment. There's been an experiment based on superconducting qubits that basically reproduce our first results in their systems. Turns out our circuits can be compressed so that you can apply 1 or 2 layers of local unitary transformations and measure everything and do the data processing only classically. So that way the experimental realization was easier, and they achieved basically the same phase diagram using their superconducting chips. Relatively more recently, we also applied the 2D generalized version of our work to recognize topological phase and apply this to the real-world data obtained from quantum simulators. And we do see that the desired information is amplified, the relevant regimes of the experiments. How much time I have? 5 minutes? Okay, cool. Okay, so I want to talk about the implications of our work a little bit. The one is it's improved algorithm for the quantum phase recognitions. The conventional approach, the most naive approach, is measuring the string order parameter over the chain. And it usually works. The issue is that if you tune the parameter so that the state goes close to the phase transition point, degrees of freedom becomes dressed or delocalized. In this case, measuring the conventional order parameter does not have enough overlap to the desired order so that we have a reduced strength and we need to repeat the measurement many times, so high sample complexity. However, in our approach, we just do the majority vote type, we just correct the matter before measuring it, therefore the number of required sample reduces drastically, especially near the phase transition point. So on the right, we see the string order parameter where the number of required samples diverges as you go to the critical point. Our QCNN also diverges eventually. However, up to the pretty close point, it stays low. And so it proves sample complexity. Another one is our variation ansatz. As I mentioned, our circuit is entirely unitary from the beginning to the end. That means upon our unitary transformation, we kind of transform all the wave function in the right phase to the wave functions where one measurement outcome should be deterministically 0. If you run it backwards, then we can generate systematically a quantum state that belongs to the same phase. Third one is the existence of multi-scale string order parameter. So our work can be understood by measuring Z after unitary, but in the Heisenberg picture, it could be understood as measuring some complicated operator at the level of physical layers. Turns out that complicated operators is linear combination of many different string order parameters at the different ending points and product of many different string order parameters with some positive and negative coefficients canceling each other so that we can extract our information agnostic to the, even near the critical points. It also has implications to the machine learning. Turns out, if there exists observable, whether local or non-local, so that the expectation value is separated for the gap systems and in the other phase, so the expectation value is separated by some value, so that's called the gap, not the spectral gap. Then we can prove, based on our previous work, that there exists an efficient machine learning algorithm to identify the phase. So our work, even you don't use it in practice, it serves as a proof that there could be a machine learning approach that able to learn our the observables efficiently and then use. So it justifies using the machine learning. With that, so this is my summary slide. So we talked about convolutional neural network applied to quantum recognition problem. The type of physical message I want to deliver is a connection between RG flow and nested error corrections. And there are many other open questions. Thank you so much.
Are there any questions?
Very nice talk. I wonder, can you elaborate a little bit more on the difference between quantum convolution neural network and the mirror?
It's the same. The architecture-wise is the same, but the mirror is isometry. You just run on one side to the other, like generating the wave function. However, when you run it backwards, of course, the output of the qubit may not be the state that you want to have. Therefore, we are forced to make decisions about what to do with them. So in our case, we are performing measurement, and based on measurement output, we are correcting something. Therefore, the architecture shape is the same. However, operational meaning is very different.
Thank you.
Sorry, you minute to the other side.
Thank you, Soonwon, for nice talk. Quick question. You talked in the end about 2D phases, recurrent 2D phases. Does this method also work for chiral phases? Coupled with so-called order, for example, integer fraction from all?
Very good question. I don't know. As you can tell, we are heavily relying on the connection between error corrections and the existence of the fixed point wave function in 1D. My understanding is that's harder in 2D. So therefore, we don't know. I don't know any ideas. Yes, it would be nice. Yeah.
Other questions?
Yeah, so for the first part, so we know that this order parameter will have a very clear singularity at the thermodynamic limit. But here you're comparing the traditional approach to a quantum convolutional network approach for the finite size. So can I understand in terms of because of pulling the process of the convolution, you're keeping some features that is scaling invariant so that the system mimics the thermodynamic limit. So that the transition is very clear.
That's right. That's right. So we are more precise way of saying is we are distilling scale invariant property, or not scale invariant because we are in the stable fixed point of RG. We are distilling long distance properties by doing coarse graining. So our depth, as you increase the depth, our algorithm will succeed, except for like some measured zero like points. But the problem is if you increase the depth, you need to have a larger input, exponentially larger input. So that's very in parallel with our renormalization group flow.
So, the next one, so in principle, all these spaces, all these states within a given phase should be somewhat connected, right? So I was just wondering, at a technical or architecture level, what is the main difficulty of, instead of using a fixed point wave function, but just any kind of representative wave function in that phase, and try to correct an arbitrary state toward that state instead? Would that, in principle, also work?
Yes, I think there's no difference. Like fixed point is a representative, and it's easier because its properties are well known.
Right.
But our working principle should not rely on that.
Right.
Yeah.
Then, for example, for the chiral phase, we don't know the fixed point wave function, but we can use the long wave function.
That's right, but we need to design error corrections. So here, because the fixed point of our case is understood as a stabilizer state and then has some property similar to error corrections, we could intuitively figure it out. But suppose I'm given the, like say, representative wave function, like say, ruffling wave functions. How do I identify errors and then design like error correction? That's not clear to me, so that's the bottleneck, but you're absolutely right.
Thank you, everyone. Let's thank our speaker one more time.
Thank you.